Hi there, welcome back to our next edition of Chem Talks. Today we're going to start talking about our second part of the solutions unit, which deals with acids and bases. So go ahead and follow along with me. Please make sure you're taking good notes. First thing we want to do is define an acid. And an acid is a solution that has an excess of hydronium or H plus ions. This is one of the definitions of it. We'll have a couple of them, but this is our most basic definition of it. It comes from the Latin word acidus, which actually means sharp or sour, which describes the characteristics of acids. What we see is that the more hydrogen ions that a concentration has, or solution has, the higher the concentration of those, the more the acidic the solution is. So it has a lower pH when we talk about pH here. Some general properties of acids. First of all, they taste sour, which comes from the name as we just talked about. Also, they're going to conduct electricity. Remember, electricity is the movement of electrons. You have to have ions to do that. Well, H plus is an ion, so it conduct electricity well. They're corrosive. This means that they break down certain substances. Okay, they can corrode fabric, skin, paper. That's why we always say, hey, if you get acid on you in your lab, make sure you wash off your skin immediately, or if you get on your clothes, wash it off because it can eat through there. And then what we see is that some acids can react strong with metals. Maybe you remember this earlier in the year when we put magnesium ribbon into hydrochloric acid. It popped, fizz. We were able to collect that hydrogen gas that came off it. A good example there. And then what we see is it's going to turn litmus paper, or blue litmus paper, turn to red. And litmus paper is just an indicator of something being acid or base. So acids will turn blue litmus paper red. Lots of uses for acids. Many of these you're already aware of. Acetic acid is we call vinegar. Citric acid we find in things like lemons, limes. It's in sour candies. It's in soda. Absorbic acid. This is vitamin C. Okay, our body needs this to function. Sulfuric acid. You've heard of that. That's what we usually think of as being a strong acid and causing all kinds of problems. It's used in the production of fertilizers, steels, paints, plastic, all kinds of different things. And then car batteries. If you've ever had to replace your battery, maybe you've seen that corrosion on there. Now the opposite of an acid is what we call a base. And a base is a solution that has an excess of the hydroxide, the OH minus ions. Acids have hydrogen ions, bases have hydroxide ions. Another word for base is alkali. So you've maybe heard of alkaline batteries is a good example of basic. Okay. Bases, we can also define them as substances that can accept hydrogen ions, so that hydrogen ion that's produced or we have with bases gets accepted, the hydrogen ion that we have with acids gets accepted by the bases and end up making water. Some characteristics of bases, they have a slippery feel. So if you ever, a lot of cleaning products are basic, and if you ever, when you're done cleaning, your hands have a tendency to feel real slippery. They have a bitter taste to them. They're corrosive like acids, and they can conduct electricity, as we talked about alkaline batteries. Remember, it's OH minus, so that's going to help us with that as well. Unlike acids, generally the bases are not going to react with metals, and they do have a change with litmus paper. In this case, it's going to turn red litmus paper into blue, so the opposite kind of color change and that we saw with the acids. Uses of bases, like I said, one of the biggest uses is their cleaning products, soaps, ammonia. These are all good examples of basic substances. What we see is that with these products, the hydroxide ions are going to interact with certain substances such as dirt and grease and help break them up. Chalk and oven cleaner are other examples. Another one is like Drano, or for clogged drains. Those are basic as well. Our blood is a slightly basic solution. It's just barely basic, but it is basic. When we talk about acids and bases, we have a way of measuring how acidic or how basic something is, and that is going to be on our pH scale. pH simply is a measure of how acidic or basic a solution is. Okay? The pH scale ranges from 0 to 14, with acidic solutions having a pH value below 7, and technically we can go below 0, but we generally don't see it, so we can actually have a pH below 0. A pH, obviously if something has a 0, is very acidic, means it has a high amount of the hydrogen ions in it. A pH of 7 is considered neutral, it has an equal amount of hydrogen ions and hydroxide ions, and then anything above 7 is going to consider to be basic. So here's an example if we look over on the side here. 0, things like hydrochloric acid can be 0. Lemon juice, which we would consume lemon juice, has a pH of 2. Even tomatoes are 4. You talk about some people have reactions to tomatoes. What's because it's acidic. Milk is slightly, milk is slightly acidic. Things that are basic, baking soda, soap, ammonia, drain cleaners down there. Other ones, another example of it, we talk about battery acid, lemon juice, all these different examples. So what I want you to understand is that things that are highly acidic have a very low number pH. So the 0 range, something that's really basic has a large pH, something around 14. So the thing about pH is it's what we consider to be a logarithmic scale. If you remember anything about logs from math class, logs are based on a change in 10. So a change in 1 pH unit represents a 10-fold change in the acidity of a solution. This means that if a solution has a pH of 1 and a second solution has a pH of 2, the pH of 1 has 10 times more hydrogen ion concentrations than the 2 does. Remember, the lower the number, the higher the ion concentrations. So a step from 1 to 3, 1 to 2 is 10, 2 to 3 is another 10, so that's 100 change there. So pH of 1 has 100 times more the hydrogen ion concentration than does a pH of 3. Something else we talk about when we talk about acids and bases, we already mentioned this a little bit, are indicators. Indicators are substances that can tell if a solution is acidic or basic. And we talked about the properties of acids and bases already. We talked about litmus paper. There's blue litmus paper and red litmus paper. When we put those in a substance, it will change color and let us know, hey, this is acidic or basic. The problem with indicators in general is they can't give a real accurate pH. They can tell us if something is acidic or basic, but they don't give us really accurate. Some of them we'll look at can give us actually a closer range, say it's between 3 and 4 or 7 and 8, something like that. One example of an indicator is phenolphthalein. Phenolphthalein, when it's in a acidic solution, is clear. When it becomes basic, it turns pink in color. So that lets us know, hey, we're now in the basic range, meaning we're greater than 7. Doesn't tell us exactly what pH we are, but it does let us know that we are basic. So it's colorless and acidic, and then pink in basic solution. Another example is red cabbage juice. You just take a red cabbage, you cut it up and boil it down, and you can get a variety of colors out of it, anywhere from a reddish pink all the way up to green, based on the pH of solution. This is just a natural indicator. It's pretty easy to make. So here's a list of common indicators. Oops. And as you can see, each indicator works in a specific range. Now we do have some called universal indicator, which is kind of what red cabbage juice is, and it'll work in a wide range of these, and it changes color throughout. But remember, the pH indicators give us a general idea of what the pH is, not an exact one. Here's some more natural ones. Apple skins will do it, beets, blueberries, a bunch of fruits and vegetables will give us this natural indicators. So let's go back to defining them. Early on we defined an acid as a substance that produces hydrogen ions, and a base is something that has hydroxide ions. This is what we call the Arrhenius definitions. Okay, so Arrhenius defined acid as a substance that produces hydrogen ions when dissolved in water. A base then is a substance that produces hydroxide. Arrhenius was an early scientist studying these. Now, there's some limitations of these. So today, what we do is we look at acids and bases slightly different. We use what's called the Brownstein-Lowry definition. This is our main one that we use. And it defines an acid as a proton donator. It means it's going to donate an H plus ion. A base then is a proton acceptor. It's going to accept that proton into it. And this definition takes into account some of the limitations of the Arrhenius definition. So this is the one that we use today for the most part. So we can see here, in this case, a Brownstein-Lowry is an acid, is a proton donor, which means it's going to give a proton. The base is going to accept it. So if we look at NH3 here, NH3 on the other side becomes NH4. So it gained a base, it gained a proton. So in this case, NH3 is our base. H2O changes over here to OH because it gave up a hydrogen. So this is going to be our acid because it's donating the proton. So you have to look at the not only the reactants but the products to figure out which one is going to be which. So like I said, NH3 is our base, and then water is going to be our acid. We call the NH4 its conjugate acid, and we'll get into that in just a little bit. Conjugate acid is what is formed when a base gains an acid, because if we look at this, if this were to react, it could easily drop off one of these hydrogens, go back to NH3. In that case, it would be donating an H+, which would make it an acid. And that same thing, water here can easily can pick up a hydrogen and become a base that way. We'll get into those a little bit more. So we talked already about dissociation when we talked about solubility. Well, dissociation simply is a process in which compounds separate or split into smaller particles. So if we look at an acid dissociation, we'll let HA be our acid. It's going to break down to A minus and H plus. There's our donating there. That's the dissociation. If we look for a base, right, we're starting with a base. It's going to join with water. Remember, base is going to gain it, so it becomes HB plus and then OH minus. So kind of seeing here, this goes back to our Arrhenius definition. If we look at it from its gaining a hydrogen or accepting hydrogen, there's our Brownstein-Lowry definition. Now, we often talk about strong acids and strong bases. And when we talked about molarity, we talked about the strength of a compound is what molarity measured. Well, when we talk about strong acids and bases, it's slightly different. What we see is strong acids more readily release the hydrogen proton into the water. It means they're going to release that H pretty easily. Okay, basically it's going to 100% dissociate or 100% break apart in the water. If we had 100 molecules of hydrochloric acid, all 100 of those would break apart into H plus and Cl minus. Okay, or if we did it with H2SO4, all the H2SO4 that we start with is going to break down to H plus and SO4 minus. A weak acid, on the other hand, then, is something that gives up the proton with a lot of difficulty, meaning it doesn't want to break apart. A good example of this is acetic acid or vinegar. If we had 100 molecules of acetic acid, probably only maybe 10 of those, 5 of those are going to break apart. Most of the time, it's going to stay as acetic acid. And so we call those a weak acid. Strong bases are the same thing. Strong bases are going to readily release hydroxide in the water, okay, and the hydroxide is then going to grab a hold of it. A good example of this is sodium hydroxide. Okay, sodium hydroxide will pretty much break apart 100%, dissociate into sodium plus OH. Now, OH generally is going to join up with a proton to form water. Weak bases, same as weak acids. They don't break apart a whole lot. So the big thing to remember is strength does not equal concentration. We could have an acetic acid with a molarity of 10 molar, but it doesn't mean it's a strong acid. It's a weak acid because it doesn't break apart. With acids and bases, strength is related to its dissociation, or how much of it breaks apart. So keep that straight. So here's an example. If we have a strong acid, what we see when it goes into solution, we're going to get equal amounts of the proton and the acid part. And here's a weak acid, what we see is we get still, when it goes into solution, we're still going to have mostly the weak acid, or in this case, it's going to be the weak base. And it's going to break apart into the two different parts. So strong acids totally dissociate, weak acids hardly dissociate at all. So if we look at this example, this is 100% dissociation of an acid, HA. So here's our acid, okay? When it goes into solution, you can see it all breaks apart. All the red and blue separate. Now, would it be conductive? Well, of course, because the H plus is going to be an ion, an A minus. So we have lots of ions in there conduct electricity. If we look at a partial dissociation, or a weak, what we can see is in here we have mostly the acid. We have a few molecules, 2 of them it looks like, that have broken apart, 3, but for the most part it's pretty weak. And what we can see is it's not really going to conduct electricity very well because there's not a lot of ions in there. So very poor at conducting electricity. So here's what you need to know. There are lists of, what do we got? 1, 2, 3, 4, 5, 6 strong acids. Hydrochloric acid, hydrobromic, hydroiodic, nitric acid, sulfuric acid, and perchloric. You need to memorize those. Let me say that again. You need to memorize these 6 strong acids. You will be tested on that. Strong bases, what you need to know is this, is anything that combines with hydroxide from group 1 or 2, that's starting with lithium or beryllium, is going to be considered to be a strong base. So group 1 and 2 metals. So you need to be able to recognize strong bases or explain that it's anything from group 1 or 2 metals combined with hydroxide, but you do need to memorize these 6 strong acids. Okay, so copy those down, put them in your mind. You need to memorize those. So pause the video now, make sure you get those. All right, we talked a little bit earlier about conductivity. What we said is that strong acids and strong bases are strong conductors of electricity. They dissociate almost 100%, which means that they can produce lots of ions, so they can conduct electricity very well.